So last time we were talking about Lupital's rule. We're still talking about Lupital's rule. Specifically, we're going to talk about the exponential indeterminate forms today. So these three things are what we're looking at. Hey, Kate, thank you. We're looking at forms that look like 1 to the infinity. Oh, this pen, really? Pen? Sure. Sorry. Okay, sure. Or 0 to the 0, or infinity to the 0. Now, again, when I write this, I don't really mean that to that. I mean, that's kind of just a way of saying, like, for example, if I were looking at this limit, the limit as x goes to infinity of 1 plus 2 over x to the x power, I would call that, thank you, a 1 to the infinity indeterminate form. Thanks. Because the part inside the parentheses here is going to 1 as x goes to infinity, and the exponent here is getting infinitely large. And I want everyone to realize the words. I want everyone to know this limit's not going to be 1, because you don't have 1 times 1 times 1 times 1 times 1 a bunch of times. You have a number that's really, really close to 1, but a little bit bigger than 1 times itself a bunch of times, which means it's going to grow. Infinitely large? Maybe, maybe not. Let's find out. There's kind of two schools of thought as how to do this sort of limit. One way to do it is like this. You can do the limit as x goes to infinity of e to the natural log of 1 plus 2 over x to the x. And then you can just keep it the whole way. Some people like to do like that. Other people like to just look at the natural log part and then rewrite the answer at the end as e to the thing. So let's do it this way. And kind of the key step to recognize here is that we can write the limit of e to the something as e to the limit as x goes to infinity of the natural log of 1 plus 2 over x dx. We can't use Lupital's rule yet, but we will be able to shortly. So I'm going to bring that x down in front. Get the limit as x goes to infinity. Sorry, I wrote it wrong a little bit. See, I always want the limit out in front. It doesn't really matter, but I guess I should really write it as e to the limit as x goes to infinity of x times the natural log of 1 plus 2 over x. And then finally, thank you, e to the power of the limit as x goes to infinity. I'm going to bring this x down to the bottom. So I'm going to write it as the natural log of 1 plus 2 over x over 1 over x. All of that effort to get an expression where I can now actually use Lupital's rule, because this exponent here is a 0 over 0 type. The denominator is 1 over x, which is going to 0. The numerator is the natural log of 1 plus 2 over x. 2 over x is going to 0. 1 plus 0 is 1. Natural log of 1 is 0. So this top part here is definitely, or I should say this exponent here is definitely a 0 over 0 type. And this is always the process for doing these ones that are exponential types, is you're always doing e to the natural log and then taking the limit of the exponent until you can make it look like something where you can use Lupital's rule. So then, using Lupital's rule, we get e to the limit as x goes to infinity of, all right, derivative of the top, derivative of the bottom. It's going to come up so many times, I'm just going to say it up here. The derivative of 1 over x is the derivative of x to the minus first, which is minus x to the minus 2, or minus 1 over x squared. Whichever way you want to slice it. But I like writing as negative 1 over x squared. So the derivative of 1 over x is negative 1 over x squared. And the derivative of natural log of some stuff is 1 over 1 plus the stuff, or 1 over the stuff, sorry, times the derivative of the stuff. If the derivative of 1 over x is negative 1 over x squared, what's the derivative of 2 over x? Exactly, we're just multiplying by 2. And the nice thing that happens with a lot of these examples in particular is the x squareds cancel. You can totally rewrite it if you want. Say it's e to the limit as x goes to infinity of 1 over 1 plus 2 over x times -2 over x squared times the reciprocal of this, which is x squared over -1. And then you can be like, oh yeah, those x squareds definitely cancel. Or you could have just canceled them there. That happens a lot. And now we're left with a limit we can evaluate. As x goes to infinity, this 2 over x goes to 0. So we're left with e to the 1 over 1 plus 0 times -2 over -1, which is just e squared. So this limit is e squared. The number is approaching 1, or I should say 1 plus 2 over x is getting 1 fast enough so that it kind of balances out the x getting the power getting infinitely large in such a way that that number gets closer and closer and closer to e to the second power. It's kind of neat. Another way of writing this, actually, let's do another problem. So let me show you a slightly different way of writing this all out so you can see it differently. Should we do that one? Let's do that one. Let's look at the limit as x approaches 0 of 1 plus 3x to the 1 over x power. This one still has the same format, although it looks a little different, but it's still a 1 to the infinity type. And what I would suggest do, so instead of doing, well, I'm still actually going to write, I'm going to find the limit as x goes to 0 of e to the natural log of 1 plus 3x to the 1 over x. But then what I'm going to do is I'm actually just going to do that limit by itself. Meaning I'm going to do this part down here. The limit as x goes to 0 of the natural log of 1 plus 3x to the 1 over x. It doesn't matter if you want to separate this part out or not. Right? I kind of like to do it this way because it feels like I don't have to carry this e to the thing the whole way through. But if you do it this way, you have to remember that once you get your answer, that's not really your answer. Your answer is going to be e to whatever this limit is, just like I've written it there. Similar process. We bring the power down. You have the limit as x goes to 0 of 1 over x times the natural log of 1 plus 3x. And you might say to yourself, I have an infinity times a 0, but really you have a 0 over 0. Because you could really just write this as the limit as x goes to 0 of the natural log of 1 plus 3x over x. Same thing. And then we use Lupital's rule because we have a 0 over 0. It's weird, like there's no one on Zoom. It's kind of bizarre. So limit x goes to 0. The derivative of the top is 1 over my stuff times the derivative of my stuff. And I didn't even leave room for the derivative of the bottom because the derivative of the bottom is 1. You can really, I guess you can write over 1 if you really want to. I don't think you need to. And then we're going to get, well, x go to 0, I'm going to get 3 over 1 plus 0. It's going to be 3. So my final answer is e to the third. Questions so far? Okay, let's look at a couple more examples. So another indeterminate form is infinity to the 0. Like the limit as x goes to infinity of the natural log of x to the 1 over x power. That's definitely infinity to the 0 form. I'm going to say this as many times as I can. For any of these exponential forms where you have an x in the exponent, you always want to do this thing where you take the natural log. And you can either do it the first way I did it or the second way I did it, where you do it as e to the natural log of your stuff the whole way through, or you can take the natural log of the thing and then at the end say your answer is e to the that. I kind of like doing it the second way. I didn't always, but I've kind of grown accustomed to it. So we're going to look at the limit as x goes to infinity of the natural log of the whole thing. And then our answer is going to be e to the limit of that. Right? Because we're really thinking about doing e to the natural log of this stuff. So here's e to the natural log of the stuff we're actually trying to find the limit of. So we're going to work with this. And again, the whole reason we did this is so we can bring the 1 over x down. So the limit as x goes to infinity of 1 over x times the natural log of the natural log of x. Which I would, no, yeah, I would just re-express as the natural log of the natural log of x over x. And here's something you'll see, you'll maybe learn with experience, is that this is definitely going to go to 0. Even without the second natural log of x over x, if you just think about the graphs for a second, natural log of x does this kind of deal, x does that, right? So y equals x is growing way, way faster than y equals natural log of x. The natural log of x is the slowest thing you've ever seen in your life. Like it grows so incrementally slowly, it's unbelievable. It still does go to infinity. Like it takes, I mean, forever, literally, but you know, it takes a lot longer than all the other ones. This one's going to be 0, but let's actually see it. So using Lupital's rule, we get the limit as x goes to infinity of, all right, 0 at the bottom is 1. 0 at the top is 1 over the stuff times the derivative of the stuff. And every time after we use Lupital's rule, we should then check to see, can I evaluate the limit? So can we let x go to infinity now and get something? Well, if x goes to infinity, we're going to get 1 over infinity here, which goes to 0, and 1 over infinity here, which goes to 0, and 0 times 0 is 0. This is definitely going to 0. So what's our answer? Thank you. Yes, exactly. So our limit as x goes to infinity of the natural log of x to the 1 over x power is e to the 0, which is 1. Yeah. And then, sure, let's kind of go the other way. Let's look at the limit as x goes to infinity of x to the 1 over natural log of x. Kind of funky looking. Is it so? I want to warn you. Whenever you're doing these limits, you might not always be able to use Lupital's rule. Right? Someone might write a thing where they mean for you to check it before you just throw Lupital's rule at it. So I should definitely look at this and ask myself, can I even use Lupital's rule? Obviously, I can't how it's written. Right? It's not a fraction. It's not a 0 over 0 or infinity over infinity. So even if I could use Lupital's rule, I'd have to do some work. But I don't want to waste my time. And it really is true that the only 3 types of exponential indeterminate forms are 0 to the 0, 1 to the infinity, and infinity to the 0. Anything else is not indeterminate. So this is infinity to the what? Where's that exponent going to? Yeah, so it is an infinity to the 0. Okay, that's one of our 3 exponential indeterminate forms. So we're going to go ahead and use Lupital's rule here. So I'm going to write this as, I'm going to do it the other way. I should say the limit is x goes to infinity of e to the natural log of x to the 1 over x. Oh, sorry, 1 over natural log of x. Apologies. And then look what happens here. This is the limit as x goes to infinity of e to the, if I bring that power down, I've got 1 over natural log of x times natural log of x, which is, what's my power going to be? What's 1 over natural log of x times natural log of x? It's just 1. It's kind of funky. What's really funky about this is if you graph this, if you graph, why would I say if you graph this? Let me just show you the graph because it's kind of cool. Cool, yeah. Oh, that's sorry. Looking at you guys homework assignments. Check this out. Grant and I discovered this a few years ago when we were doing stuff. There's the graph of y equals x to the 1 over natural log of x. It's always e. Well, except for when x is negative, because you can't take the natural log of a negative. If you graph y equals e, it's the same. It's kind of weird that x to the 1 over the, I'm sorry, the x to the 1 over the natural log of x power. This is not important at all. I just think it's kind of neat. Sometimes that's what you get to hear about. This is equal to e if x is greater than 0. How bizarre. Kind of funky. You can kind of, like, you can do some work to kind of see it's true, but it's not that important, but it is an example. So the reason we came up with this example is because most of the time when you have an infinity to the 0 kind of thing, you end up getting 1 as your answer. We were looking for an example where you didn't get 1. So here's an example where we don't get 1. Okay. Let's look at some other examples. What time is it? Okay, we got time. How about limit as x goes to infinity of the square root of x plus 5 over the square root of x plus 5. Whoops. So it's definitely infinity over infinity. So we can certainly use Lupital's rule. So if I use Lupital's rule, let's see what happens. I might write these as 1/2 powers instead. So let's see, let's do this as the limit as x goes to infinity. The derivative of x plus 5 to the 1/2 is 1/2 times x plus 5 to the negative 1/2 times 1 over the derivative of the square root of x, or x to the 1/2 is 1/2 x to the negative 1/2. And I'm going to rewrite this. The 1/2s cancel. And I'm going to write this as the limit as x goes to infinity of, I'm going to write this as the square root of x on top, the square root of x plus 5 on the bottom. Okay. Still infinity over infinity, so I guess we'll do it again. So let's see what happens if we do it again. The derivative of the square root of x is 1/2 x to the minus 1/2. The derivative of square root of x plus 5 is 1/2 times x plus 5 to the minus 1/2. And oh no, if I simplify this, I'm essentially back to where I started. The square root of x plus 5 on the top, square root of x on the bottom. I'm kind of in a loop here. If I keep going, I'm going to keep getting the same thing. Now, writing it like doing these couple steps actually does get us to a place that's slightly better. So we can't keep going. I mean, we can, but we can't keep doing L'Hopital's rule and get anything meaningful. So sometimes, even though you can use L'Hopital's rule, it's not going to help you at all. At this point, what we want to do here is, well, we can write this as one square root. We can write this as the limit as x goes to infinity of the square root of x plus 5 over x. And then we can simplify that as a limit as x goes to infinity of the square root of x over x is 1, 5 over x is that, and then the 5 over x goes to 0. It's 1. So sometimes if you can get stuck doing L'Hopital's rule in an infinite loop. I think this next problem has the same sort of problem. Let's look at the limit as x goes to infinity of 3e to the 2x plus e to the x over e to the 2x plus 4e to the x. Definitely infinity over infinity, right? Top's getting infinitely large, bottom's getting infinitely large. So let's use L'Hopital's rule. See, the derivative of the top is going to be 3e to the 2x times 2, so 6e to the 2x plus e to the x. And the derivative of the bottom is going to be 2e to the 2x plus 4e to the x. Still infinity over infinity. And I think you can imagine that if I keep doing this, I'm going to keep getting infinity over infinity, right? This top part is going to just multiply by 2, and right, so the next one would be the limit as x goes to infinity of 12e to the 2x plus e to the x over 4e to the 2x plus 4e to the x. Still infinity over infinity. I'm not going to get anywhere doing this. So instead, we have to use some other tools. In this case, when you have something like this with exponentials, you kind of want to think about which thing is getting the biggest the fastest, or what's the dominating term. This is very similar to the limit as x goes to infinity of, say, something like 5x cubed plus 7x plus 1 over 9x cubed plus 4x squared plus 8. Everyone should be able to tell me what the limit of this is without doing any work. You guys know what it is? 5 over 9. Right? And now the work you could do in the past, in the beginning of this quarter, would be to divide everything by x cubed. Because x cubed is the thing that's dominating the top and dominating the bottom, right? It's the thing that grows the fastest of x cubed and 7x and 1. The same thing is what we're going to do here. In the numerator, the e to the 2x term is what's growing the fastest of the e to the 2x and the e to the x. And in the denominator, the same thing, e to the 2x is growing faster than 4e to the x. So we're going to divide everything by e to the 2x. So dividing by e to the 2x, here's what I've got. So I've got 3. I should say I've got the limit as x goes to infinity of 3 plus e to the x over e to the 2x. You could write it as e to the negative x. I'd much rather write it as 1 over e to the x. That just seems better to me. And then over here, I'm going to have 1 plus 4 over e to the x. I suppose there's kind of two schools of thought about how to write things. I definitely like to write things like in this previous problem. I definitely like to write negative powers like when I'm going to have a derivative, but I like to write roots when I'm trying to evaluate the limit. I feel like writing like this, I can't tell what's getting big, what's getting small. Writing like this, I can totally tell what's getting big, what's getting small. But writing like this is better for taking further derivatives. So same idea here. Writing it like this is definitely better to see, is this thing getting big or small? I think it's easier to see that e1 over e to the x is getting small versus e to the negative x. But if I was going to have to use L'Hopital's rule again, I'd probably rather write this as e to the negative x and take the derivative of. That's going to be 3 plus 0 over 1 plus 0, which is 3. Then you need to use L'Hopital's rule at all. Sometimes L'Hopital's rule is not the best rule. Sometimes it is. Look at a few more examples. I was only, unless there's something else you guys want to hear about, I was planning on talking about L'Hopital's rule all the time, L'Hopital's rule. Unless there are other things you want to hear about. We didn't do one of these yet. Let's do the limit as x goes to 0 from the right of sine x to the 1 over x power. Oh, sorry, 1 over natural log of x. Apologies. Let's just write a new piece of it. So actually, let me go back to that one for just a second. We could do this one. What kind of form do I have? Where is sine going to? 0. How about the exponent? 1, infinity, 0. 1 over x, if x is going to 0, 1 over x is going to infinity. Is this an indeterminate form? Actually not. This is determined because you essentially have something. So again, right, this doesn't mean you actually have 0, it means you have something close to 0, right? But something that's getting very, very small, smaller than 1, times itself a bunch of times. That's going to be 0. So 0 to the infinity is not an indeterminate form. It's fully 0 every single time. Which is nice. In fact, anything that's less than 1 and not approaching 1 to the infinity power is going to go to 0. So for example, if someone said, what's the limit as x goes to infinity of, I don't know, 3/5 to the x power, you don't have to do any work here. We know that limit's going to be 0 because you have something times itself a bunch of times and that thing is smaller than 1. Or even if it's a little more complicated, like the limit as x goes to infinity of, sure, let's do that one. 3 to the x plus 1 over 5 to the x plus 7. All right. So now I do need to use L'Hopital's rule one step. You could. Okay. There's a number of ways to do this, right? I see using L'Hopital's rule first. That's my first thought because infinity over infinity. If we use L'Hopital's rule, let's see what we get. So what's the derivative of 3 to the x? It's been a little while. It's 3 to the x times natural log of 3. And the derivative of 5 to the x is 5 to the x times natural log of 5. And then at this point, hopefully you can see, if I use L'Hopital's rule again, I'm just going to get stuck in this loop, right? This is infinity over infinity. If I do L'Hopital's rule again, the derivative of the top is just going to give me another multiple of natural log of 3. The derivative of the bottom is just going to give me another multiple of the natural log of 5. So if we did it one more time, we would get the limit as x goes to infinity of 3 to the x times natural log of 3 times natural log of 3 over 5 to the x times natural log of 5 times natural log of 5. Not particularly helpful. So now we have to be like, well, okay, I could also see that this is going to be the limit as x goes to infinity of 3/5 to the x, 3 to the x over 5 to the x, times a constant that's not going to matter. And that's going to go to 0. Another way you could have attacked this problem would have been to divide everything by 5 to the x in the first place. You could have said that's the limit as x goes to 0 of 3 to the x over 5 to the x plus 1 over 5 to the x over 5 to the x over 5 to the x plus 7 over 5 to the x. And then that's going to be 3 to the x over 5 to the x is 3/5 to the x. That's 1 over 5 to the x. That's 1. That's 7 over 5 to the x. And each of these things go to 0. Even 3/5 to the x. So you get 0 plus 0 over 1 plus 0, which is 0. So I don't know, a lot of time, not infrequently, if you have something rational like this, and L'Hopital's rule is not getting you anywhere, a good method of attack is to try dividing everything by the biggest thing, the thing that's growing the fastest. That'll often get you where you want to go. But now it's actually the problem. I was trying to write down last time, I didn't write down correctly. The limit as x goes to 0 from the right of sine of x to the 1 over natural log of x power. Okay, so I'm going to look at the limit as x goes to 0 from the right of the natural log of sine of x to the 1 over natural log of x. And then whatever my answer is, my actual answer is going to be e to the that. So this is going to be e to the something, where this is going to be that something. All right, so what am I going to do? I'm going to bring down that exponent. So this is going to be the limit as x goes to 0 from the right of 1 over natural log of x times the natural log of sine of x. I feel like this first step I'm always kind of wasting some space, right? I should just write it as natural log of sine of x over natural log of x. Probably better. Natural log of sine of x divided by natural log of x. And now I can use L'Hopital's rule because I have a natural log. So actually, I should ask you all, what kind of indeterminate form do I have? Do I have a 0 over 0 or infinity over infinity? Well, what's natural log of 0 going to? I guess actually I have a negative infinity over negative infinity form. Because the natural log of 0 is going to negative infinity if you think about the graph of the natural log of x. Doesn't really, I mean, it matters that you know that you can use L'Hopital's rule before you use L'Hopital's rule. I don't want you to use it when you can't. That's what I'm trying to point out. Let's see. So we're gonna get the limit as x goes to 0. The derivative of this is 1 over sine of x times cosine of x. The derivative of this is 1 over x. All right. Oh, this is going to be funny. Maybe. Whenever I see this, I really don't want to have fractions and fractions. I would much rather write this as the limit as x goes to 0 of cosine of x over sine of x times x over 1. To me, that's a better way to go. I'm trying to always, if I can't use L'Hopital's rule, or I should, oh, gosh, words. If I can't plug in the limit right away, which I can't here, right? If I plug in 0, sine of 0 is 0, I get 1 over 0. If I get 1 over 0, I definitely can't plug that in. Then before I start trying to use L'Hopital's rule again, I should try and simplify, right? Taking the derivative of this part, the derivative of this part, probably not going to get me anywhere good. In fact, you could use L'Hopital's rule there, and here's what you would get. All right, cosine over sine is cotangent. The derivative of cotangent is negative cosecant squared x. The derivative of 1 over x is negative 1 over x squared. Things are not getting better here. This is getting worse. So before you start trying to use L'Hopital's rule a second or a third or a fourth time, simplify your stuff. This is going to be a little bit better. It's still a 0 over 0 type, or I should say it is a 0 over 0 type. So I can use L'Hopital's rule. So using L'Hopital's rule, the derivative of sine is cosine. I always like to do the easier part first. So I'm not just doing the top or the bottom because I'm doing the bottom first because it's easier than doing the derivative of the top. The derivative of the top, I am going to have to use the product rule. So derivative cosine is negative sine of x times x plus now cosine of x times 1. And now if we let x go to 0, we get sine of 0 times 0 plus cosine of 0 over cosine of 0. So we end up getting 1 as our limit, which is not our final answer. Our final answer is e to the 1. All right. Kind of neat. Yeah. I'm sorry. So I want you guys to try these two problems. So the limit as x goes to 0 of, sure, x minus tangent x over x minus sine x. And if you finish that one, try this next one. Work on those for like 3-ish minutes, we'll say. In case the derivative of secant squared is tripping you up a little. So it is 0 over 0, right? Check, plug in. And if we do Lupital's rule one time, is it still 0 over 0? Yeah. It is, right? Because you've got secant of 0, which is 1, and cosine of 0, which is 1. So that's also 0 over 0. So we do it again. And then things start to get really gnarly. Oops, I should write the limit. So the derivative of secant squared, well, I wrote it over here. It's the derivative of secant x 20 squared, which is going to be 2 secant x times secant x tangent x. But it's negative. And the derivative of negative cosine is positive sine. And here's where you could use L'Hopital's rule again, because it's still a 0 over 0. The sine of 0 is 0 and tangent of 0 is 0. You really don't want to take the derivative of secant squared x times tangent of x. That seems terrible. So this is where we're going to say, well, I could write this as the limit as x goes to 0 of, I'm just going to write it all out. I've really got -2 times secant, which is 1 over cosine x, times secant, which is 1 over cosine x, times tangent, which is sine x over cosine x. And then if that's all divided by sine, that's the same as being multiplied by what? 1 over sine. And then we can have a sine cancel. And that takes care of our 0 over 0 problems. So then we get 1 over 1 times 1 over 1 times 1 over 1 times -2, which is -2. Interesting. What about the second one? Can I use L'Hopital's rule here? Yeah? Nay. No, I can't, right? Because what do I get when I plug in 0? Sine of 0 over e to the 0. That's looking like just good old 0. Done. Thank you. So don't let yourself get into the mindset of like, oh, just L'Hopital's rule every time, right? So they'll someone, not everyone, but some teachers like to be trickier than others. Someone might try to trick you and be like, oh, here's one they'll definitely think they have to use L'Hopital's rule a few times, and they don't, right? Plug it in, you get 0 over 1.